Catechin, Wikipedia audio. Catechin /Kaettn/ is a flavin 3-OL, a type of natural phenol and antioxidant. It is a plant secondary metabolite. It belongs to the group of flavin 3-ols, part of the chemical family of flavonoids. The name of the catechin chemical family derives from catechu, which is the tannic juice or boiled extract of Mimosa catechu. Catechin possesses two benzene rings and a dihydropyran heterocycle with a hydroxyl group on carbon 3. The A ring is similar to a resorcinol moiety while the B ring is similar to a catechol moiety. There are two chiral centers on the molecule on carbons 2 and 3. Therefore, it has 4 diastereoisomers. 2 of the isomers are in trans configuration and are called catechin, and the other 2 are in cis configuration and are called epicatechin. Chemistry. The most common catechin isomer is the catechin. The other stereoisomer is catechin or N-catechin. The most common epicatechin isomer is epicatechin-epicatechol, L-acocatechin, L-epicatechol, AP-catechin, 2,3 cis-epicatechin or epicatechin. The different epimers can be distinguished using chiral column chromatography. Making reference to no particular isomer, the molecule can just be called catechin. Mixtures of the different enantiomers can be called catechin or DL-catechin and epicatechin or DL-epicatechin. Catechin and epicatechin are the building blocks of the proanthocyanidins, a type of condensed tannin. Catechin, catechin, epicatechin, epicatechin. Moreover, the flexibility of the C ring allows for 2 conformation isomers, putting the B ring either in a pseudo-equatorial position or in a pseudo-axial position. Studies confirmed that catechin adopts a mixture of A and E conformers in aqueous solution, and their conformational equilibrium has been evaluated to be 33:67. Oxidation. As flavonoids, catechins can act as antioxidants when in high concentration in vitro, but compared with other flavonoids, their antioxidant potential is low. The ability to quench singlet oxygen seems to be in relation with the chemical structure of catechin, with the presence of the catechol moiety on ring B and the presence of a hydroxyl group activating the double bond on ring C. Electrochemical experiments show that catechin oxidation mechanism proceeds in sequential steps, related with the catechol and resorcinol groups, and the oxidation is pH dependent. The oxidation of the catechol 3,4-dihydroxyl electron donating groups occurs first, at very low positive potentials, and is a reversible reaction. The hydroxyl groups of the resorcinol moiety oxidized afterwards were shown to undergo an irreversible oxidation reaction. The lacase/APS system oxidizes catechin to oligomeric products, of which proanthocyanidin A2 is a dimer. Reference: D. Doublet, DD, doublet of doublets, M. Multiplet, S. Singlet. 2.49, 2.82, 3.97, 4.56, 5.86, 5.92, 6.70, 6.75, 6.83. 273 water loss, 139 retro-Diels alder, 123, 165, 147. Catechin and epicatechin as well as their gallic acid conjugates are ubiquitous constituents of vascular plants, and frequent components of traditional herbal remedies, such as Uncaria rhynchophila. The two isomers are mostly found as cacao and tea constituents, as well as in Vitis vinifera grapes. Spectral data. Natural occurrences. The main dietary sources of catechins in Europe and the United States are tea and pome fruits. In food. Metabolism. Biosynthesis. Biodegradation. Humans. Catechins and epicatechins are found in cocoa, which, according to one database, has the highest content of catechins among foods analyzed, followed by prune juice and broad bean pod. Acai oil, obtained from the fruit of the acai palm, contains catechins. Epicatechin and catechin are among the main natural phenols in argan oil. Catechins are diverse among foods, from peaches to green tea and vinegar. Catechins are found in barley grain where they are the main phenolic compound responsible for dough discoloration. The taste associated with monomeric catechin or epicatechin is described as slightly astringent, but not bitter. The biosynthesis of catechin begins with Ma4-hydroxycinnamoyl CoA starter unit, which undergoes chain extension by the addition of 3-malonyl-CoAs through a PKC8 pathway. 4-hydroxycinnamoyl CoA is biosynthesized from L-phenylalanine through the shikimate pathway. L-phenylalanine is first deaminate by phenylalanine ammonia lyase forming cinnamic acid, which is then oxidized to 4-hydroxycinnamic acid by cinnamate 4-hydroxylase. Chalcone synthase then catalyzes the condensation of 4-hydroxycinnamoyl CoA and 3 molecules of malonyl CoA to form chalcone. Chalcone is then isomerized to naringenin by chalcone isomerase, which is oxidized to iridoxyl by flavonoid 3-hydroxylase and further oxidized to taxifolin by flavonone 3-hydroxylase. Taxifolin is then reduced by dihydroflavonol 4-reductase and leucoanthocyanidin reductase to yield catechin. The biosynthesis of catechin is shown below. Research. Leucocyanidin reductase uses 2,3-trans 3,4-cis leucocyanidin to produce catechin and is the first enzyme in the proanthocyanidin specific pathway. Its activity has been measured in leaves, flowers, and seeds of the legumes Medicago sativa, Lotus japonicus, Lotus uliginosus, Hedysarum sulfurescens, and Robinia pseudoacacia. The enzyme is also present in Vitis vinifera. Catechin oxygenase, a key enzyme in the degradation of catechin, is present in fungi and bacteria. Among bacteria, degradation of catechin can be achieved by Acinetobacter chalcoacidicus. Catechin is metabolized to protocatechoic acid and fluoroglucinol carboxylic acid. It is also degraded by Bradyrhizobium japonicum. Fluoroglucinol carboxylic acid is further decarboxylated to fluoroglucinol, which is dehydroxylated to resorcinol. Resorcinol is hydroxylated to hydroxyquinol. Protocatechoic acid and hydroxyquinol undergo intradiol cleavage through protocatechoate 3,4 dioxygenase and hydroxyquinol 1,2 dioxygenase to form beta-carboxy-cis, cis-mucinic acid, and mallyl acetate. Among fungi, degradation of catechin can be achieved by Chaetomium cuprum. Catechins are metabolized upon uptake from the gastrointestinal tract, in particular the jejunum, and in the liver, resulting in so-called structurally related epicatechin metabolites. The main metabolic pathways for SREMs are glucuronidation, sulfation and methylation of the catechol group by catechol-O-methyltransferase, with only small amounts detected in plasma. The majority of dietary catechins are however metabolized by the colonic microbiome to gamma-valerolactones and hippuric acids, which undergo further biotransformation, glucuronidation, sulfation, and methylation in the liver. The stereochemical configuration of catechins has a strong impact on their uptake and metabolism, as uptake is highest for epicatechin and lowest for catechin. Nanoparticle methods are under preliminary research as potential delivery systems of catechins. Cocoa catechins are under preliminary research for their potential to affect the risk of cardiovascular diseases. One limited meta-analysis showed that increasing consumption of green tea and its catechins to 7 cups per day provided a small reduction in prostate cancer. Biotransformation. Biotransformation of catechin into taxyfolin by a two-step oxidation can be achieved by Burkholderia sp. Catechin and epicatechin are transformed by the endophytic filamentous fungus Diaporthy sp into the 3,4-cis dihydroxyflavin derivatives, 3,4,5,7,34 hexahydroxyflavin and 3,4,5,7,34 hexahydroxyflavin, respectively, whereas catechin and epicatechin with a 2S phenyl group resisted the bioxidation. Glycosides. Leucoanthocyanidin reductase uses catechin, NADP and NH2O to produce 2,3-trans 3,4-cis leucocyanidin, NADP, and H+. Its gene expression has been studied in developing grape berries and grapevine leaves. Centuries ago, catechin-containing extracts were thought to be useful for treating heart diseases, and an effect on the permeability of capillaries was shown in 1936. Limited evidence from dietary studies indicates that catechins may have an effect on endothelium-dependent vasodilation, which could contribute to normal blood flow regulation in humans. Green tea catechins may improve blood pressure, especially when systolic blood pressure is above 130 mmHg. Due to extensive metabolism during digestion, the fate and activity of catechin metabolites responsible for this effect on blood vessels, as well as the actual mode of action, are unknown. Bioactivity studies. Vascular function. Possible immune effects. The European Food Safety Authority established that cocoa flavonols have an effect on vascular function in healthy adults by concluding, cocoa flavonols help maintain endothelium-dependent vasodilation, which contributes to normal blood flow. Data from observational cohort studies have not shown a consistent association between flavin 3-OL intake and risk of cardiovascular diseases. A meta-analysis also indicated that green tea catechins may favorably affect cholesterol. Depending on dose consumed, catechins and their metabolites can bind to red blood cells and possibly induce release of autoantibodies, resulting in hemolytic anemia and renal failure. This resulted in the withdrawal of the catechin-containing drug Catechin, used to treat viral hepatitis, from the European market in 1985. Catechins released into the ground by some plants may hinder the growth of their neighbors, a form of allelopathy. Centaurea maculosa, the spotted knapweed often studied for this behavior, releases catechin isomers into the ground through its roots, potentially having effects as an antibiotic or herbicide. One hypothesis is that it causes a reactive oxygen species wave through the target plant's root to kill root cells by apoptosis. Most plants in the European ecosystem have defenses against catechin, but few plants are protected against it in the North American ecosystem, where Centaurea maculosa is an invasive, uncontrolled weed. Catechin acts as an infection-inhibiting factor in strawberry leaves. Epicatechin and catechin may prevent coffee berry disease by inhibiting oppressional melanization of Calidotrichum cahoui. Botanical effects.